Hello everyone, and welcome to today's video on radians. So I'm just going to make one video. I don't know how long it's going to be, but I will put timestamps in the description. I'm going to start by going through radians, talk about why they're useful, how we use them, what they're used for. There are three main things to cover for that, and then what I'll do is I'll go through the three questions. So what I have here is I have access to the textbook. So if ever I need to refer to anything in the textbook, I can flick through that. So we might spend a bit of time talking about that. What else have I got? I've also got a calculator, which we will be obviously having to use, and I also have the solutions to the three questions. So with all of that being said, let's get started. So I think what I'll do is work my way through the PowerPoint, and then when I feel like it's necessary, I might pause and maybe go a little bit off tangent. Okay, so radians. So as I say, there'll be timestamps in the description. If you're very confident now on radians, then clearly you can just skip ahead. But I'm going to go through radians. I'm going to go through how I would teach radians. So first of all, what is a radian? Well, let's start this animation. Okay, so that's 1 degree, because there are 360 degrees in a full turn, obviously. 1 radian is a little bit bigger than 1 degree. How a radian is defined, and it's in that picture there on the screen, is if you've got a circle, radius r, really could be any radius, and then you make a little sector. This sector, the arc length for it needs to be the same length as the radius. And so what that does is it defines a particular angle. It defines 1 radian. Now, the symbol for radian can be a little c. It can also be rad, as it is in the PowerPoint. Often, we don't use any symbols at all. The only thing to be aware of now is that when you see an angle or a trigonometry question where degrees aren't being used, you have to assume now radians, and you must now always put a degrees symbol if you are talking about degrees. Okay, so I'll say more about that in a bit. So anyway, this is 1 radian here. It's literally defined by this shape here, and so the question is how many radians are in a full turn, and how big is it in degrees as well? Like, that's another good question to ask. So how many radians are in a full turn? So if I was obviously using degrees, I would have drawn something a lot smaller. I would have drawn a 1 degree, and it would be the size such that 360 of them would fit together and make a full turn. How many of these do I need to make a full turn? Well, that's best answered first of all if you're not already aware of the answer. You might want to pause and have a think. The clue would be how many of these lengths here, which is the length of the radius, how many of those lengths there are going to fit around the circumference. So that this is where this says it here, right? Thinking about how many radii around the circumference we can go. Yeah, there's your answer. 360 degrees is 2 pi radians. So the answer is 2 pi radians in a full turn. Now, if you think about different units of, say, length, you've got centimeters and you've got inches. It's not that controversial to have a decimal number in terms of a conversion, right? So there's 2.54 centimeters in an inch. The actual line that you're measuring is the same line whether or not you're using centimeters or inches, but the number that you write down will be different. And so if I'm choosing to use radians, a full turn, I would put the number 2 pi. If I would have to round that as a decimal, obviously. It's better to leave it as an exact answer. And if I was using degrees, I would use 360 degrees. So the question is okay, well, what's the size of 1 radian in degrees? So you're going to do this by kind of equating 2 pi radians with 360 degrees and going from there. So 2 pi radians is 360 degrees. So in terms of a little ratio, we've got radians to degrees. We're going to have 2 pi radians in a full turn because there are 2 pi radiuses in a circumference. The formula for the circumference is 2 pi r. So 2 pi radians, there'll be 2 pi of these that you need to fill the whole circle. So that's 360. And so one thing I might do is, pi radians is 180 degrees. So a straight line is pi radians. Pi on 2 is a right angle. Pi on 3, it will be 60 degrees. So I'm just going to come back to this and divide both sides by 3. Pi on 4 would be 45 degrees. And pi on 6 would be 30 degrees. Okay, so that's these are kind of your nice angles with it. If you think about trigonometry, right? These are your nice angles, and these are them in radians. Now I asked, what if I actually wanted this number here to be 1? If I want 1 radian, what is that in degrees? So if we go back to here, what do I need to divide both sides by to go from pi to 180 to 1 to something? I'm going to need to divide both sides by pi. So I'm going to need to do 180 divided by pi. So let's see what that is. So now I'll bring the calculator up and do 180 divided by pi. So it's about 57.3 degrees to 1 decimal place. So 1 radian is 57.3 degrees to 1 decimal place. Obviously it's going to be a decimal that goes on forever because it's involving pi, but that's how we would answer that. And then in general, if I have a number, so to convert radians to degrees, you want to times by 180 and then divide by pi. So times by 180 and then divide by pi. And if you want to convert degrees to radians, which is, I guess, kind of thing you'll have been doing already, so to convert degrees to radians, right, you times by pi and then divide by 180. So let's just sort of see that working in practice. So if I want to do pi by 6 and show that that's 30, I would have pi by 6. I've got to times that by 180 and divide that by pi, and of course I'm going to get 30 degrees. And if I wanted to do, say, 45 degrees, what is that? So 45 degrees into radians, I have to times by pi and then divide by 180. And of course I get pi on 4, or a quarter pi. So that's the definition of a radian. There's nothing more to it than that. There's 2 pi radians in a full turn. You've got to use your knowledge that there are 360 degrees in a full turn to kind of, work things out from there. In terms of how you would do this from a practical real world perspective, I'm not aware of any protractors that have radians on. Maybe they exist, I don't know. But what you would realistically do is use a normal protractor if you were really measuring an angle but wanted it in radians because you were going to do some computations and it was involving radians. You would get it in degrees first, and then you convert it to radians by timesing it by pi and then dividing by 180. Okay, so that's come from this. It's come from the definition. And so a really good question now is, well, what's the point? Like, why on earth do we bother with that? Well, before I answer that question, let's just see how the PowerPoint addresses that. So, okay, so why use radians as our unit? Well, that's a great question. Why are they better than degrees? I mean, degrees obviously do have some advantages. I mean, for a start, we're really used to them. Most people know about degrees. Most people know that 360 degrees in a full turn. They know what 180 degrees is. It's easier to understand. It's not involving pi. It's whole numbers. You know, there's lots of good reasons for it. But you're A-level mathematicians, and you're going to be doing some harder maths than you've done before. And it basically turns out that radians are a lot more useful to use and to work with. And so I'm going to try to explain why that is. So, okay, so it already comes out and says this. So we're going to see that if you plot y equals sine x, well, if you were plotting it in degrees, obviously it would go from 0 and then it would kind of go up to 90 and then down to 180. And you've got to think, actually, that's really, really not very steep, right? To go from 0, 0 along to 90 along and 1 up, that is a very, very shallow gradient, right? Right, seamless, totally seamless. So this is what I mean. So first of all, when I'm on Desmos, hopefully this is working okay. When I'm on Desmos and I just type in y equals sine x, I get this graph here. But Desmos, because Desmos is really, really clever, Desmos is assuming radians. In fact, there you can see you've got a choice between radians and degrees, and the default when you load it up is radians. Now, 0, 0 for sine. Now, sine of 90 degrees is 1, so that's actually pi by 2 in radians. So here, one of the coordinates is pi by 2, 1. That's just over 1.5 along, and I'm already up to 1. Then sine of 180 degrees is 0, but that's pi in radians, so that's down to here. Now that's only just above 3, isn't it? And so you can see it goes up and down, up and down, up and down a lot more often in radians than in degrees, because we've scaled it right down. If I plot y equals sine x, but in degrees, but on the same scale, on a totally normal scale where it's the same amount along as it is up, so on squared paper, where it's really going to go from here, 0, 0, and I'll have to scroll all the way along to go to sine of 90. So this blue line, remember, this blue line is in degrees this time. Now, I know normally when you draw the sine graph or the cos graph or any trig graph in degrees, you'll obviously rescale the x-axis. You'll normally go 0, 90, 180, 270, 360, and you'll squeeze that right up so that you do draw it going like that. But you have to have in mind what it actually looks like when you haven't scaled it like that, when you haven't squashed the x-axis up. Goes all the way along to 91. There's one of the coordinates there. And then it starts to go down. And this is what I was trying to say before. I think I probably should have... Let's go all the way to 180. Why not? There you go. Crosses at 180, 0 starts going down. You can see what's going to happen. And now, what I was trying to say before is that this gradient here is, well, it's almost flat. I mean, clearly it isn't flat. It is going uphill, but it's almost flat. Certainly around here, right? Now, what I can say is if you compare gradients in terms of the steepness of the hill, if you're lazy, you want to walk on the blue one because the gradient isn't as steep. The gradient of the red one, well, it's steeper here. In fact, it looks like the gradient is 1 there, and then the gradient is 0 here, and then the gradient is -1 here, and the gradient is 0 here, the gradient is 1 here, the gradient is 0 there, etc. And it's just basically going up and down, up and down, up and down, well, much faster in radians. That's the point. And so the question is if you actually plot the gradient function when it's in radians, well, if you go back to what I just said, at 0, 0, the gradient is 1. I mean, I'm saying it looks like it's 1. It is actually 1. We have a bit of work to do to prove that it's actually 1, but let's just sort of go with it for now. The gradient here is about 1. In fact, you can see even from there to there, those corners there, it's almost a straight line with gradient 1. So if I plot the gradient function, it would be at 0, 1. Then it would go to pi by 2, 0, right? Because at pi by 2, it's flat. It's reached the top of a hill. It's a flat gradient. Pi by 2, 0. So it's started from there and then it's gone down. And then it would be down to -1 here because the gradient is, well, this is at pi. So at pi, the gradient is -1. And so what you'd actually end up drawing is the cos graph. That's the point. You'd end up drawing the cos graph. And so when you differentiate sine x, you get cos x. And this is a really, really, really big deal. And this is only true if we're in radians. If we're in degrees, we don't get that answer. We get something related to it, and you'll learn more about that when you learn about the chain rule for differentiation. But right now, this is why we use radians. So sine x differentiates to cos x. And you could actually, as a little exercise, by the way, if you wanted to, try and work out what cos x differentiates to using a similar method to what I was doing about like plotting where it was a gradient of 1, where it was a gradient of 0, where it was a gradient of -1. You try to do it for cos x and see what you get. Okay, so then you had some questions, so we'll skip those. You have access to this PowerPoint, so you should have worked through it. I mean, even there, look, cos x. So here at 0, 1, the gradient is 0. Okay. At pi by 2, the gradient is -1. So it's down here. So what you'll end up with is a little bit like sine x, but so it needs a minus sign in front. So the derivative of cos x is minus sine x. So a little exercise for you to try to show that. Okay. I'm not going to talk about this because this is trig from year 12, where you're just going to replace 180 and 360 with pi and 2 pi. Whereabouts do the what else is it used for? Well, if you think about arc length formula and sector area formula from GCSE, so here is, okay, so if the angle is in degrees, the arc length, so just this bit here, it's a fraction, a proportion of the full circumference. And how you did that back at GCSE was, it was just n degrees out of 360 degrees multiplied by 2 pi r. right? The circumference length. Now, if instead this was in radians, so I'm going to say that n degrees is going to be theta radians. Okay, so theta is my angle in radians. So theta is in radians. What would the formula be instead? What would the formula be instead? Well, this time it would be theta out of 2 pi. So it's still a proportion, but this time it's not out of 360. It's out of 2 pi. And it's still that proportion of the circumference. So the 2 pi's cancel, and you get a much nicer formula. You get theta r for your arc length formula. And a similar thing happens with sector area. So again, you'll have n degrees out of 360 degrees times pi r squared if you want the area of this sector. But if instead I was actually doing radians and it was out of 2 pi, I have theta out of 2 pi times pi r squared. The pi's cancel, and I get theta over 2 r squared. And they're just much nicer formulas. And this formula here is after I've gone through the 3 questions and I show you one of the key results. Yeah, it's a little bit tricky, so I'm putting it at the end. This here is is basically what's going to give us that sine x differentiates to cos x. Ultimately, okay. So this is actually really useful even for later stuff. So anyway, let's keep going with the PowerPoint. So yeah, so there you go. That's that. Area. So we should have half r squared theta, or yeah, half of theta times r squared. Same thing. Now, of course, if you want the area of a segment, which is where you just want this bit, you work out the area of the sector, but then you take away the area of this triangle that's left over. Now, the area of this triangle is actually not that hard to work out if you can remember the area of a triangle formula. So that's a half AB sine C. But both A and B are R, and the C will be your theta. So this is not so bad. I mean, it's even got it here, right? A half r squared theta, that's the area of the sector. Take away a half AB, which is really r squared, because A and B are both r, sine theta. And then actually you can take out a common factor, and this is quite a nice little formula. You don't necessarily need to remember this formula because you could just do each bit separately and then take them away. I mean, you can if you want to. So all of that would have been good practice for you for sure. Oh, and then of course you had some trig equations. So I don't need to go through that because that is just what you did in year 12 in degrees, but now you're in radians. So on your calculator, you'll be in radians. Make sure you do that. And then instead of using 360, you're using 2 pi. Instead of using 90, you're using pi by 2. So the small angle approximations is really the one of the big things. So we've covered arc length and sector area. The fact that you could do those in degrees anyway, of course you can, but the formulas themselves, if your angle is in radians, then you get to use an easier formula, right? So that's an advantage. Also, one of those 2 formulas, the sector area one, is used, and I'll show you at the end of the video because I'm going to leave it to the end, is used to actually derive one of these small angle approximations. So what are the small angle approximations, and what does it even mean to be a small angle? So first of all, what small means is the smaller the better, and if you choose a smaller angle, the approximation gets more accurate. And it works on the flip side. If if your friend comes along and says, I want to be this close to the actual true answer, you can work out an angle that will work, that's small enough so that it will work. Okay, so that's what small means in this context. So I will say all of that again, and I'll put a few examples in to illustrate that. Okay, so if theta is in radians and theta is small, so again, what exactly small means, well, I'll show you in a second. Then sine theta will approximately equal theta if theta is small and theta is in radians. That's one of the small angle approximations. I'll talk about the others in a second. I just want to sort of actually show you what it means for sine theta to be small. Okay, what does that mean? So I'm going to bring the calculator up, and I'm going to make sure I'm in radians, because that would be a good thing. So we're in radians now. So if I do sine of, say, pi, that should be 0, right? Yeah. Whereas if I was in degrees, that's not going to give me 0. Okay. So anyway, sine theta is approximately equal to theta. Now, it's going to be easier, and actually it's actually where this comes from. So I'm cheating slightly, because really the small angle approximation comes from if I divide by theta. Okay, so if I divide this approximation by theta, I get this. Now this is actually a lot easier for me to test because I want to get closer and closer to 1. I want this expression to get as close as I want to 1. So let's try it. So if theta is, let's try theta is pi by 2, which of course equals about 1.57. So let's actually see what that actually is. Yeah, so about 1.57 to 2 decimal places. Now, is this small? Is this a small angle? Well, let's see. How good is it? So if I do sine of pi by 2 and I divide that by pi by 2, I get 0. So let's do sine of pi by 2 over pi by 2, and that's 0.6366. So I'll just go to 4 significant figures, so 4 sig fig. Now, is that close to 1? Well, on one hand, yes, right? It's only 0.4 away. But on the other hand, given that sine is already between -1 and 1, that's not that close to 1, is it? Pi by 2 is not small enough. But the idea is if you relax your standards, you could say, well, yeah, that's fine. That's small enough. That's close enough to 1. But you could have someone come along and say, well, no, that's not close enough to 1. You need to make this angle smaller. Okay, well, let's make this angle smaller. Let's try. So let me just write it up again here. So sine theta over theta, we want this to be nearly 1, and we need to be theta in radians and theta to be small. So let's try it for different values of theta. So let's try 0.2, let's try 0.1, let's try 0.01, and let's try 0.001. And once we've seen these in action, I'll explain again what it means to be a small angle with a little bit more precision, because obviously so far I've not really been very precise, have I? So sine of 0.2 over 0.2. So we chose a smaller angle, much smaller than 1.57. 0.2 radians, a lot smaller, and we were a lot closer to 1. So we got 0.9933. So I'm just going to make all of them 4 sig fig. Okay, so you could have someone say, oh, brilliant, yeah, that's close enough. Brilliant, super. But then you could have someone who says, well, no, I think we need to get even closer. So sine of 0.1 over 0.1 is 0. And so we closer still. We gotten a bit closer there. Sine of 0.01 divided by 0.01, much closer. And no, we'll do the last one. I mean, that is basically right there, isn't it? So there you go. And so what does it mean for theta to be a small angle? Well, more technically what it means is someone comes to you and says, I want to be this close to 1. I want to be 0.00000000001 away. That is how close I want to be. What you can then do is you can find a theta that is small enough that will work. That is what it means. So if the person comes along and says, oh yeah, I just want to be within 0.4, you go, well, great, use pi on 2, that works. But someone could come along and be a lot more, they want a lot more precision. They want to be really close to 1. And so you can pick an angle can get as close as you like. That's the point. That's the point. It's as close as you like. Now, notice what happens if I do sine of 0 over 0. Well, of course I get an error, right? Because I can't do 0 divided by 0. What this is it is an example of an expression that in the limit as theta approaches 0, we get 1. That's the answer to the limit question, right? It is getting closer and closer to 1. And it isn't technically enough to, obviously list examples. We can actually prove that the limit as theta approaches 0 of this expression actually is 1. And so that's another kind of illustration of what it means for theta to be small. It means we're taking a limit as theta gets closer and closer and closer to 0. I could also have taken some negative thetas, because sine of a negative angle is the negative of sine of the positive angle. Gosh, that's a bit confusing to say, but basically it will be a negative on the top and a negative on the bottom, and they'll cancel out and you'll still get 1. So I mean, I'll just illustrate that now. If I do sine of minus 0.001 and divide that by minus 0.001, well, that minus sign is going to come to the front of sine, and then it'll cancel top and bottom, and I'll still get, well, I'll get the same answer as I got before, right? So that's all it means, and that's this here. You times up by theta and you get this small angle approximation, which you're allowed to use when theta is in radians and theta is small enough that it's okay to use it. And of course that does depend slightly on who's judging whether or not it's close enough or small enough. So anyway, and it's also kind of highlighted here in this graph picture, which has, I guess, been on your screen for quite a while. Now the graph y equals sine x is never truly a straight line anywhere, but through the origin, it and if you kept zooming in, it would get closer and closer and closer to the line y equals x, which is just a manifestation of this, that if you look at sine theta and you compare it with theta, when theta is very small, both these things are converging to the same thing. They're both the same when theta is very, very small. I mean, they're not perfectly the same, but they're getting closer and closer and closer to being the same, which is obviously what an approximately equals means, right? They're nearly the same, and they're more nearly the same the smaller you make theta. You should try this out, by the way, for yourself, using degrees on your calculator. I'll let you pause and try that now. I'll just do it now though, so you can see. So if I do it in degrees, we're not going to get the same answer, but we are going to get something that you should recognize. Okay, so you might not recognize it like that. Let me make the calculator not be able to round anymore. Okay, so it gives you pi over 180. So you should have a think about why it might do that. Right, let's get this calculator off and move on. So, turns out there's also two other small angle approximations. Now, I won't go into the same amount of detail with cos and with tan, but I'm going to give you a little bit of an argument for the cos one. It's a little bit of a hand wavy argument, which means it's not particularly precise. So cos theta is approximately equal to 1 minus theta squared over 2. Now, for theta in radians and for theta small. Now, I'm not going to go into a full explanation of this one, like I will do with sine after I've gone through the questions. But I might just briefly show you this now. So there's two bits of maths that you're actually going to learn about in year 13, which kind of helps illustrate this fact. So I'm going to do two kind of not completely rigorous arguments to show you why this is true. So on the one hand, if we start with something we already know and square both sides, and then realize that, of course, this is 1 minus cos squared, and then rearrange, and then square root, now this is not a polynomial, right, because it's got a square root here, and what you're going to learn something about a more general binomial expansion in year 13, where you would be able to expand this as a series with increasing powers of x. Now, I'm not going to go into that now, but it turns out that if you do this, and this could be a question that's asked at A level, maybe not this beginning bit, it could give you this and say expand that in increasing powers of theta. This could be an A level question. It turns out that you can expand this and you're going to get 1 minus theta squared over 2. Let me just, I wrote the rest down just to sort of show you. So, and then minus theta to the 4 over 8 minus dot dot dot. So it goes on forever. And then the point is that if theta is really, really small, then certainly theta to the power of 4 is going to be really small, and you can pretty much ignore it. And so it's an approximation, and there's your answer. So that's that. So that's with a binomial expansion with power of a half, which is something you will learn about at A level in year 13. So I'm a bit much maybe now, but you will learn about this. The other hand wavy argument is another thing that you'll learn about is compound angle formulae, and in particular double angle formulae. So cos of 2 theta, if you look in your formula booklet, you will have a little formula for cos of A plus B. Now, a double angle formula for cos is this basically. So this is again another thing you'll learn about in year 13. So it turns out that this formula here is true. And so what can I do? Well, I can say that is cos squared. Well, that's the same as 1 minus sine squared. So 1 minus altogether 2 sine squared. And then what's the idea here? Well, cos of 2 theta is going to therefore be approximately equal to 1 minus 2 theta squared, because sine squared will be approximately equal to theta squared. And then let's not use 2 theta, let's just use theta. So I'm basically, whatever theta was, I've halved it. And so that's literally theta squared over 2. So two kind of hand wavy arguments for the cos one that basically come from the answer for sine. And then the last one is just that tan theta is approximately theta. And essentially, where does this one come from? Well, sine theta over cos theta is, of course, approximately equal to theta over 1 minus theta squared over 2. Now, if I make theta really, really small, this bit here basically disappears a lot faster than theta, because theta squared is, if you square a really small number, as a really small decimal between 0 and 1, it goes really, really small, like so small, that when theta is really, really small, this bit basically disappears until you get theta. Again, not a particularly rigorous argument, but just to kind of illustrate where that comes from. So, so you actually have got a little geometric proof here. I'm going to show you something, I guess it's quite similar, but I'll do it slightly differently at the end of the video. So when theta is small, so you know 0.1 is small, but we could go smaller. 0.01, 0.001. The smaller we make it, the more accurate the approximation, like the more it's actually, the closer it is. And so, and theta has to be in radians. So here are your questions. So I'm going to go through these now. So number 1, what have we got? So BAD has sent us C. Okay, so they're all equilateral triangles, so that helps. They are not exactly drawn to scale, I wouldn't say. It doesn't look like a circle top and bottom, does it? As in part of a circle. So I think it's if I can work out the area of one of these sectors, or rather one of these segments, and then just times that by 4. So I'm going to draw the line that goes straight down from A to C. Now the red arrow on the side there tells me that is 4. I know that this length here, so this is from A to B, so I might as well label it so you can see what I'm doing. A, C and B. Now I'm told that that's 4. And I'm also told that that's 4. So all of these are 4. And then I've got this where C is literally the center. So this is a segment. Like that's it. So what I'm going to do is I'm going to get an answer to this segment, then times it by 4. So I'm going to do a half r squared theta minus a half r squared sine theta, right? Like that's what I'm going to do, where theta is in radians. I'm going to get my answer and then times it by 4. So I guess in an equilateral triangle, that angle is 60 degrees. Now 60 degrees is a third of 180, so that's a third of pi, so that's pi on 3 there. So I'm going to have a half r squared times pi by 3 minus a half r squared times sine of pi by 3. Now maybe I've forgotten my exact trig values. Sine 60 is root 3 on 2, isn't it? So that's what sine of pi by 3 is. So let's just confirm that. So sine of pi by 3, oh, I've got to be in radians. So sine of pi by 3 will give me the same answer, because I'm in radians on the calculator. It's going to give me the same answer as if I wrote sine of 60, but being in degrees. Now sine of 60 is root 3 on 2. So that here is root 3 on 2. So let's tidy this up a bit. So I get pi. I'm going to keep r. I'm going to keep writing r, even though I know r is 4, because why not? So 2 times 3 is 6. That's that. And then what's this? That's root 3 r squared over 4. Now, how does it want it written? Okay. Well, I guess what I would do now is probably, well, I could do two things. I can times this answer straight by 4, because really I want 4 of these, right? So timesing this by 4, I'm going to have 2/3 pi r squared minus root 3 times r squared. R squared is really 16, so I'm going to have 32 on 3 pi minus 16 root 3. And then let's have a think. So I want to just take 2/3 out, don't I? So equals 2/3, and then that would be 16 pi. And then 16 times 3 over 2. Root 3. So 16 times 3 is 48. Halved is 24. So 24 root 3. So is that the answer? Yes. Brilliant. There we go. So that's that. That's clearly that there's loads of ways of answering that question. What could you do? Let me have a think. So what have you got? You could work out. So if you follow the mouse, start at C. So if you look at the shape CD, A but via the arc, B but via the arc, and then back to C, you've got a big segment. Sorry, not a big segment, big sector with, I guess, angle 120 degrees. And clearly that's the same shape but reflected upside down of ADCBA. So you could work out that sector area and double it, and then just take away 2 lots of this middle shape. I think there are literally loads of ways of doing this. But anyway, that's the way that I've done. It's literally applying the formulas in the PowerPoint. So anyway, that's that. Let's have a look at number 2. Okay, so number 2. So when theta is small, I guess theta also has to be in radians. It doesn't say that in the question, but PowerPoint's all about radians, so I guess it's safe to assume. So let me just remind you what these small angle approximations are. So it turns out that sine theta is approximately equal to theta in this situation, and the smaller you make theta, the more accurate this is. Cos theta is approximately equal to 1 minus theta squared over 2. And tan theta is also approximately equal to theta. So there you go. Those are the small angle approximations. And so we want to ask about this expression here under these assumptions that theta is small and theta is in radians. Okay, so all I'm going to do is I'm going to write like a wiggly equal sign, right? This is approximately equal to 1 plus, now sine theta is approximately equal to theta. Tan theta is approximately equal to theta. So tan 2 theta is approximately equal to 2 theta. Now let me give just a small indication of why that must be. If theta is small, and you can make it as small as you like, basically, while still being above 0, you know, put as many 0.0000 in there as you like. If theta is small, doubling it, it's still small. So tan of 2 theta is going to be approximately equal to 2 theta. So that's why I've replaced it there. And then 2, now cos of theta is approximately equal to 1 minus theta squared over 2. So cos of 3 theta, for similar reasons to up here, that if theta is small, then so is 3 theta, because tripling of something that's tiny still keeps it tiny. So cos of 3 theta is going to be 1 minus, and then it will be in brackets 3 theta getting squared. And of course this is actually being doubled, isn't it? So I need to be careful with my brackets here. 1 minus 3 theta getting squared over 2, and then minus 1. So this is the approximate equals under these assumptions. And then on my next line, I'm just going to tidy that up. So I'm going to write equals now, because it's this expression here that I'm sort of continuing with. Whatever I end up with will be, if you trace back through, will be approximately equals to the original expression. So on the top, I have 1 plus 3 theta. And on the bottom, let's have a think. Well, 2 times 1 is 2. 2 times that fraction will just cancel the 2 on the bottom. And 3 theta all squared is 9 theta squared, and then take away that 1. So a little bit more tidying up. That's a difference of 2 squares. In fact, to be fair, it was already written as a 3 theta being squared, wasn't it? So that's 1 plus 3 theta over 1 minus 3 theta, 1 plus 3 theta. So cancels top and bottom, leaving you with the answer. Write that again. So there you go. Hence write down the value of this when theta is small. So when theta, so in this situation, you want to set theta equals 0 in a question that's phrased like that. So part B, when theta actually is 0, this equals 1. So the idea is that the complicated expression to begin with, as theta approaches 0, this approaches 1, this whole expression. And it's really, really difficult to see that to begin with, isn't it? Like, if I make theta really, really small, what does this get closer and closer and closer towards? Well, it gets closer and closer and closer towards 1. So that's that. And then last question. Goodness, right. What have we got? We've got a big shape. Okay, so part A for number 3. The area of that sector, the sector formula is a half theta r squared. If, for example, if theta was 2 pi, if it was the whole circle, half of 2 pi is pi, and you recover pi r squared, the formula for the area of the whole circle. So anyway, in this question, this is a half times, and because we're in radians, we get to use this nice formula. That's the point. Because we're in radians, we get to just literally go a half times 1.4 times 5 squared. So, well, whatever that is. So we'll bring up... Oh, the calculator's been on the screen the whole time. Well, fair enough. Fair enough, right. So, 0.5 times 1.4 times 25. So 17.5. So that's that. Let's just, I'll just bring the answers up for a sec, by the way. All right, there we go. Right, so that's the mark scheme for number 1. So it's maybe going to be a bit tricky to mark because it's you know, lots of little parts. That's number 2, and okay, 17.5. There you go. Right, part B. Find the size of the angle DBC. Okay, so that's just cosine rule. So a squared, so mine went blank there, so a squared equals b squared plus c squared minus 2bc cos a. So what have we got? We've got 6.1 squared is 5 squared plus 7.5 squared, take away 2 times 5 times 7.5 times cos a. I'm not talking about the a in the question though, obviously. I'm talking about my a from this. So anyway, let's work this out. So 6.1 squared minus 5 squared minus 7.5 squared, all divided by minus 2 lots of 5 lots of 7.5. And if I do cos inverse of that, can I fit it there? Cos inverse of this, it's going to be my angle. So let's type that in. So and we want it in radians, so I must make sure the calculator is in radians. 6.1 squared minus 5 squared minus 7.5 squared. Just put that bracket there and then go back. Minus 2 times 5 times 7.5. So 0.943 radians to 3 decimal places. I can confirm that that is correct. And then part C, I need to have a closer look at this. Right. So the reason I was pausing there was I was trying to work out how we're going to figure out the area of that right angled triangle, but there's probably a few ways of doing it. But the way that I just thought of there, because I mean we already have the area of the sector, and getting the area of the triangle on the right is fairly straightforward now because we've got the angle. So we can use the area of a triangle formula. So anyway, look, here I've got this, and it's like, okay, well, what's the area? Well, we don't know, do we? Well, we're going to figure it out because we can figure out this here. This is going to be pi minus 1.4 minus 0.943. I'm going to go right ahead and assume that I get to use 9.43. Although we could be more accurate, I suppose. This is the thing with this sort of question. It's like, you know, you don't want rounding errors, but then it's also not immediately obvious if they're going to allow it because you've just given a previous answer to 3 decimal places. But anyway, I think we're going to err on the side of caution here and be accurate. So this is, in fact, I mean, I can literally do pi minus 1.4 minus the previous answer, actually. So that's pretty nice. So this is 0.7983916, and we'll leave it like that. That's going to be enough decimal digits for it to not matter too much. Although, to be fair, we could probably even use the exact answer or save it in our memory, so we can do that as well. So that's that there. Now all I'm going to need to do is work out, say, this length here, and then I can use my area formula. So we have the hypotenuse, we want the adjacent, so I'm going to use K. So the adjacent is 5 times cos of the angle we just did, so this. So what's that? So literally 5 times cos of the previous answer. So that's 3.489297,888. Okay, and so the area of this triangle is 1/2 times this answer times 5 times sine of this. And as I said, you know, at this point I could probably, there's lots of other things you could do, but this is what I'm going to do. So 1/2 times the previous answer on my calculator times 5 times sine of 0.79839916. So I get that area there is 6.2478895. So I'm not gonna worry about rounding until the end. So that's that, and I need to add that to 17.5. So I've got 6.2478895, add 17.5. So that's this triangle over here. Then this is the sector, and then I've got kind of to do the last bit there, which is going to be 1/2 times 5 times 7.5 times sine of 0.943201. So let's just do that. 1/2 times 5 times 7.5 times sine of 0.943201. So 15.177. Let's go 0.35. Why not? And then add all of this up. So add that to 17.5. And then add that to 6.2478895 to get a final answer. So this is summing up. And to 3 significant figures, I get 38.9. Now this is where I'm like, I really want this to be the right answer, because I do not want to have to re-record this. So let's put the word solutions up. Okay, 38.9. There we go. Super. Okay. So that's clearly not the easiest thing in the world to set out, and it's also really annoying with all of the decimals there, but hopefully that was okay. Hopefully you followed what I did. Yeah, any further questions, by the way, please just send me an email. Now, we've reached the point of the video where I'm going to show you. So this bit now is optional. I mean, the whole thing, the whole video was optional, but this bit of the video is the most optional, because what I'm going to do here is I'm going to prove that when you measure theta in radians, sine theta is approximately equal to theta. Okay, I'm going to show you how to do that. So, I'm just going to get some more paper. Ooh, and I better hide that. Okay, so there's going to be a bit of editing to do in this, I'm sure. So anyway, here's what you do. I didn't look too much at what it did in the PowerPoint, because well, I guess there's nothing wrong with it. Just this is what I would have done in class. So what you do is you draw a little coordinate axis and you put a unit circle on there. Well, rather just this quarter of it. And so what have you got? So this is the unit circle, so this is length 1. And then put an angle in, theta. And so what we're going to say is we're going to say theta is in radians. Right, so I am measuring it in radians. If you want to think of that as being measure it in degrees with your protractor and then convert it to radians, feel free to think that. Just like a line can exist and be both something that's in inches and also something that's in centimeters, is also fine as well. So theta, I'm going to think of it as being in radians, and my calculator is going to be in radians. When I talk about how big it is, I'm going to say a number, and the number is going to be in radians. So theta is in radians. So what we do now is kind of put on a little bit extra here. So I'm going to go up to there so that I actually create a right angled triangle here that's kind of gone out of the circle. Do you see that? I've just extended that line upwards. Now, let's first of all ask the question about what's that coordinate there. Well, that's by definition of the unit circle, cos theta sine theta. The coordinate is cos theta sine theta. Okay, if I go along cos theta and I go up sine theta. So what's this coordinate here? What's that coordinate? Hopefully you can understand how I kind of arrive at this coordinate, right? You follow along this radius, and you jump out of the circle, and you keep going until you form a perpendicular with the x-axis back towards this coordinate here on the circle. So how are we going to answer, first of all, this question is to notice that we are in the situation of similar triangles. So angle, 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 it's a 90 degrees just like this one is. So they're both 90. They share that theta, they literally share it, so they certainly have that angle in common, and therefore these two angles are the same as well. Okay, so by angle, 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 this triangle here is similar to this triangle here. And so therefore sine theta over cos theta, so the ratio sine theta over cos theta will equal this height here over 1. So I'll say that again. What have I done? Where's this come from? Sine theta, this height here, divided by cos theta, this length here, will be the same as, because they're similar triangles, this, this question mark over this length here. And that length there is 1, because we're in a unit triangle, unit circle. Well, it doesn't take a lot to see that sine theta over cos theta is tan theta, and tan theta over 1 is tan theta. So it turns out that this is tan theta. I mean, it's 1 along and then tan theta up. So this is actually this is one of the places where tan theta appears on the unit circle. Okay, kind of pops out over here. It's this height here. So anyway, so let me just write in that coordinate. So this is 1 along and tan theta up. And of course, theta is in radians. So now that we've established that and that this here is tan theta tall, I'm going to compare three areas. So I might have to draw this picture again, to be fair, because there's a lot on it. So I'm going to draw the picture again where I can be a little clearer, because there was a lot on that one. So okay, what we're going to do is we're going to look at this area. We're going to so actually let's do that first. Let's do that first, actually. So the area of this triangle here, well, what's the base length? The base length is 1, and what's the height? The height is sine theta. So the area of the yellow triangle is literally 1/2 times base times height. Okay, so that's that area there. All right. Now, the next area along that we're going to consider is going to be the area of the sector. Which, no matter how big theta is, as long as it's not 0, and remember, we're not actually talking about theta being 0, we're just talking about theta being small eventually. For just a positive theta, an acute angle, this green sector has a bigger area than the yellow triangle because of the segment, because of the extra bit in the segment. So what I've got here is I've got an area. So this one's the little triangle. Let me just write this. Little triangle. This one's the sector. And what the formula for the area of a sector is 1/2 r squared theta. I'll tidy all of this up in just a sec. Okay, so that area there is bigger than that area there. And then last of all, let's use let's use this. So the pink triangle is obviously got the biggest area of all, right? It's got this extra bit on the outside. So just so there's the big triangle. Now this area is 1 times, how tall was it again? It's tan theta tall. So it is 1/2 of the base times the height. And as long as, you know, if theta is an acute angle, I can make theta be smaller if I want. But if theta is an acute angle, then for sure the area of the little triangle here is less than the area of the sector, which is less than the area of the big triangle. Hopefully that sounds fair enough. And if we are measuring our angle in radians, then the sector area is going to be, well, we would use the sector area formula for the theta being measured in radians. So this won't work if we're measuring it in degrees, right? Because we'd have an angle out of 360 times pi r squared, right? And it won't give us the same answer, right? It's because we're measuring it in radians that I get to just write this down. Okay, it's a lot nicer if it's in radians. So let's tidy this up a bit. A half times 1 times sine theta is just sine theta over 2. A half times 1 squared times theta is just theta over 2. And a half times 1 times tan theta is just tan theta over 2. So this is definitely true if theta is an acute angle and theta is measured in radians. So I'll write that. Theta is acute, theta is in radians. Okay, so let's manipulate this inequality, right? So let's just double everything. That seems like a good idea. So sine theta less than tan theta. Let's divide everything by sine theta. I mean, clearly there's a bunch of things you could do, right? But let's divide everything by sine theta. Now, when theta is an acute angle, I am and would also, if it's an acute angle, then it's a positive angle that's between 0 and 90 degrees, right? That's between 0 and pi by 2 radians. So if I divide an inequality, well, if I divide in general, I want to make sure I'm not dividing by 0, but of course I'm not dividing by 0 because theta isn't 0 and sine theta isn't 0. Theta is also not negative and sine theta is also not negative. So it won't flip the inequalities and I won't have a division by 0 error. So I'm going to divide everything by sine theta. So 1 is less than theta over sine theta less than, now tan theta is sine theta over cos theta. When I divide that by sine theta, I just get 1 over cos theta. Now, one good property of inequalities is if you take the reciprocal of an inequality, it flips the inequality. So for example, 2 is less than 3, but if you take the reciprocal, you get a half is greater than a third. So what I'm going to do is I'm going to take the reciprocal. So the reciprocal of 1 is still 1. The reciprocal of this is sine theta over theta. And the reciprocal of this is cos theta. Now, I'm just going to sort of write it the other way around, just so it's a bit tidier. So this is not the absolute final thing we're going to do, but it's kind of the final form of our inequality before we do something to it. So what I'm going to do to this inequality is I'm going to take the limit as theta goes to 0 across the whole thing. I can do that. I can take the limit as theta goes to 0, limit as theta goes to 0, the limit as theta goes to 0. And actually, if you look at the middle is actually, if I take the limit as theta goes to 0, this is the thing we're trying to work out. We're trying to see what is the limit as theta goes to 0 of sine theta over theta. Because if that was 1, I could multiply it by theta and I'd have my answer. So anyway, maybe you don't fully follow all of that. Maybe you do. Either way, it's okay, because I'm just going to show you what the next step is, and it's not that unreasonable. Okay, so I'm going to take the limit as theta goes to 0 of everything. And the point is the inequality holds true for all these positive you know, very small but positive angles. So I'm just going to ask what happens to it if I take the limit as theta goes to 0. Like the inequality at every single stage is still valid. It's still valid. So this is a valid thing to do, even with an inequality. Okay, so I'm just taking the limit as theta goes to 0 of each 3 of these things in the inequality. It's the same inequality, but I've stuck lim theta goes to 0 in front of each thing. Right, let's deal with the easy one first. So this one here is really easy, right? If theta goes to 0, what happens to the number 1? It just stays the number 1. Like, there's not a theta there in the first place, so that just stays as 1. This middle bit is the thing we're actually wondering about. But what happens when theta goes to 0 of cos theta? Well, cos of 0 is just 1. And as theta gets closer and closer to 0, cos theta gets closer and closer to 1. And when theta actually is 0, cos theta is 1. So what we have here is we have a situation where sine theta over theta, the limit as theta goes to 0 is literally sandwiched between 1 and 1. So suppose maybe to make this a little easier to digest, I could have started with less than or equals 2's in the first place, right? So that's okay. The point is this is sandwiched between 1 and 1, so what does that have to be? So this thing has to be 1. So the limit as theta goes to 0 of sine theta over theta is 1. So in a less precise way, for small theta, sine theta over theta is approximately 1. This is really what this phrase means. It means this. And then, last but not least, I'll multiply it by theta and get my answer. Right, and remember that's for theta. Had to be in radians, otherwise that sector area formula would not have been as nice. So this is for theta in radians, and of course theta small. Right, hopefully, I don't know how long all of this is. It's going to take a little bit of editing, but hopefully that's been helpful. Hopefully the timestamps have helped. If you have any further questions, please get in touch via email.